And welcome back as we continue our cosmic journey. Previously, we had looked, of course, at how different star systems form, but let's go ahead and take it back towards our own for a minute and look at how planetary evolution might have happened within our own system. So the first thing we need to kind of take a look at is geological activity. We have seen a wide range in the level of geological activity on our own terrestrial planets and icy moons. Internal sources such as activity require energy. And this energy is either in the form of primordial heat that's left over from the formation of the planet, or from the decay of radioactive elements in its interior. The larger the planet or moon, the more likely it is to retain its internal heat, and the more slowly it will cool. Jupiter's moon Io is an interesting exception to this rule. Rather than relying on the primordial heat or radioactive elements, it's actually getting its source heat from the gravitational flexing of its interior by the tidal pull of Jupiter, largely due to the proximity next to the planet. Now, what are the stages in the geological history of a terrestrial planet, such as Mercury, Earth, Venus, Mars, or even our own moon? Well, in the image of right, time increases downward along the left side, where the stages are described. The smaller the body, the more quickly it passes through these stages. The moon, for example, was internally active until about 3.3 billion years ago, when it became geologically dead because its major volcanism had ceased. The mantle cooled and became solid, and internal seismic activity has declined to almost zero. By comparison, Earth and Venus are much larger masses, with Earth using plate tectonics to rework its surface, and Venus modifying its surface using a form of blob tectonics, where we have materials that burst through the surface. And again, if we look here, the cycle we talked about, we have accretion, heating, and differentiation, which is, of course, at the very kind of beginning of a cycle. You have formation of solid crust and heavy cratering. Then you have some widespread mare-like volcanism. Then you go to reduced volcanism, possible plate tectonics, which is, of course, where we are looking with Venus and Earth. Then you have mantle solidification, end of tectonic activity, which you can see is right here where Mars and Mercury are kind of floating around. And then you have a cool interior with no activity, which is, of course, our moon. Another thing that we have to look at is elevation differences. The mountains on the terrestrial planets owe their origins to different processes. On the moon and Mercury, the major mountains are ejecta, thrown up by the large basin-forming impacts that took place billions of years ago. Most of the large mountains on Mars, though, are volcanoes, produced by repeated eruptions of lava from the same vents. There are similar but smaller volcanoes, of course, on Earth and Venus. However, the highest mountains on Earth and Venus are the result of compression and uplift of the surface. On Earth, this crust compression results from collisions of one continental plate with another, resulting in various mountain ranges. So let's take a quick look at the highest mountains on Mars, Venus, and Earth, because it's a nice good comparison since we know that these have some similar features geologically. On Venus and Earth, the maximum elevation differences between these mountains and their surroundings tends to be about 10 kilometers. Olympus Mons, in contrast, which is on Mars, towers more than 20 kilometers above the surroundings and nearly 30 kilometers above the lowest elevation areas on Mars. Mountains can rise much taller on Mars because Mars has two things going for it. It has less surface gravity, and there's no moving plates, so these hotspots tend to stay in one spot and continuously pour out new material. So let's go ahead and take a quick closer look at Olympus Mons here. The largest Martian volcano is seen from above in this spectacular composite image at right, compared from the many different Viking orbiter photographs. The volcano itself is nearly 500 kilometers wide at its base and more than 20 kilometers high. In fact, Olympus Mons is so large because the crust, again, remains stationary. Mars doesn't have plate tectonics with respect to the underlying hotspot that would actually allow that material to eject. And so a single volcano continued to grow for hundreds of millions of years. Also, as Mars has less surface gravity, much higher elevation heights can easily be supported because it's not going to have that force of gravity to necessarily cause the same compression effect. Now, as we just mentioned, gravity has less impact on Mars because gravity actually can help determine the shape of different objects. The same kind of calculation that determines the limiting height of a mountain can be used to ascertain the largest body that can have an irregular shape. Gravity tends to pull all objects into what it considers the most efficient shape, where all the outside points are equally distant from the center. And when we look at things in outer space, planets and larger moons are nearly all spherical because the force of their gravity is kind of pulling them into a sphere. It's trying to find that most efficient shape, and it just has to be, if everything's trying to find equal distant points, it's going to tend to be pretty round. The smaller the object, though, the greater the departure from the spherical shape, which is why if you look, for example, these asteroids here in this picture, you'll notice that they're much more unusual shape. They're not necessarily very round. Another thing we can talk about is atmospheres. The atmospheres of the planets were formed by a combination of gas escaping their interiors and the impacts of volatile rich debris from the outer solar system. Now, each of the terrestrial planets must have originally had very similar atmospheres. But if we take a look at Mercury, Mercury doesn't have an atmosphere. Well, that's because it was too small and too hot because of its proximity to the sun to really retain its own gas. Now, the Moon probably never had an atmosphere either, since the material composing it was depleted in volatile materials. The predominant volatile gas on terrestrial planets is currently carbon dioxide, but initially there's probably also hydrogen-containing gases. Now, most of the light hydrogen atoms escaped, leaving behind the oxidized atmospheres we see today on Earth, Venus, and Mars. Now, what about water? Water is a very important thing. Well, the fate of water was different on each of the planets depending on its size and distance from the sun. Now, very early on in its history, Mars apparently had a thick atmosphere with abundant liquid water, but it could retain those conditions and eventually the remaining water froze. On Venus, the reverse process took place, with a runaway greenhouse gas effect leading to the permanent loss of water. Only Earth has actually managed to maintain the delicate balance that permits liquid water to persist on its surface. Now, with the water gone, Venus and Mars each ended up with an atmosphere of about 96% carbon dioxide and a few percent nitrogen. On Earth, the presence first of water and then of life led to a very different kind of atmosphere. First off, the CO2 was largely removed and deposited into marine sediments. The proliferation of life forms could then photosynthesize, and eventually lead to the release of more oxygen than natural chemical reactions can remove from the atmosphere. As a result, Earth finds itself with nitrogen as the most abundant gas, and it's also the only planetary atmosphere that contains free oxygen. It's just like O2 molecules just floating around, and that's primarily what, for example, our bodies use in order to complete their respiratory processes. Now, when we start looking at atmospheres elsewhere, in the outer solar system, Titan is the only moon with a substantial atmosphere. Now, this object must have contained sufficient volatiles, such as ammonia, methane, and nitrogen, to actually form an atmosphere. Today's Titan's atmosphere consists primarily of nitrogen. Compared with those on inner planets, temperatures on Titan are too low for either carbon dioxide or water to be in favor for. With these two common volatiles, frozen and solid, it is perhaps not too surprising that nitrogen has ended up as the primary atmospheric constituent. And so we can, of course, use this foundation from our terrestrial planets and moons to really start searching for life. One of the motivations for exploration of our planetary system is to search for life. Mercury, Venus, and the moon are really not suitable. Neither are most of the moons in the outer solar system. Furthermore, the gas giants, we start looking at the giant planets in our own system, well, they don't have solid surfaces. And they're going to fail the test for habitability. So the search for habitable environments has focused on the presence of liquid water. Earth and Europa both have large oceans, though Europa's ocean is covered with a thick crust of ice. Mars has a long history of liquid water on surface, although the surface today is mostly dry and cold, though there is strong evidence for subsurface water on Mars, which means it's underneath that initial crust that we see. Enceladus might have the most accessible liquid water, which we often see squirting in space by means of geysers. And Titan is far too cold for liquid water, but its thick atmosphere and hydrocarbon lakes actually might lend us to being the best place to search for unknown life,